patient listener, viewer, welcome to the 8th tutorial in this series on trigonometry. I do hope that you're finding this helpful. The last tutorial where we sort of motivated the graphs of the functions was on the long side, and plus, it may have just been a bridge too far, possibly. This is what we ended up with. It looks like a very complicated set of pictures, but the thing that I wanted you to get out from this was that when you repeatedly see in the future these graphs of the sine of x, the cosine of x, and the tangent of x, that you won't see them as mysterious, that you'll have a sort of a good sense of where they come from. This circle construction is an excellent way to motivate the function sine, cosine, and tangent. We're going to talk more about the properties of these functions in the next two tutorials when we talk about solving trigonometric equations. But in this tutorial, I want to talk about a tricky topic that is examined, which is what happens if we sort of push these curves around. You might call it transforming these functions. And I'm just going to concentrate on sine x. I'll just push sine x around, but everything I say can be related to cosine and also tangent. But to be honest, it's rare that you'll be asked about pushing tangent around. It's more transforming sine and cosine. So I'm going to focus on the sine of x. And let me write a really ugly equation down, and don't panic. It's not something that you're going to be asked about, I don't think, in any exam, but it just contains all the different ways that we can push this function around. Okay, so let me just write this for sine. I have to remember to write a curly x because I tend to write just a cross, but that gets confused with the times symbol, so I'll try to remember to keep writing a curly x for x. Right, so this is the sine function, but I've tried to indicate all the different things that you can actually do to the sine function, and what we're going to do in this tutorial is just take them one by one and see the effect of them. You can multiply the sine function by a number. You could take the sine function of a number times x. You can shift x by a number, or you can shift the whole function by a number. So a, b, c, and d are numbers which would have different effects on the graph of y equals sine x. And we'll just take them one by one. In fact, I might try and just divide up this page into the 4 pictures that we'll end up with. Okay, so let's start with this one, multiplying sine x. So let's imagine we wanted to draw a graph of y equals 3 times the sine of x. Okay, that's fine. So, and we're asked to take x between 0 and 360. So I'll just quickly indicate this. So we have our 90 degrees and a 180, 270, and I am just doing sketches here. These are not meant to be fancy pictures. So let me just put the ghost of sine x on here because that would be helpful. Remember, sine x goes between -1 and 1. And it has this shape, and I'm sort of going to draw it as a dash curve just to remind you. The more you deal with these functions, the more used you'll be to the shape and the fact that sine x goes through 0 at 180, that it has its maximum at 90, and so on and so forth. Now, this is sine x. And if we have 3 times sine x, what that's really saying is that at every point, we take the value of sine x, but then we multiply it by 3. So if we're at 0, 0 times 3 is 0. But at 90 degrees, where sine x has the value 1, we're now multiplying that by 3, and we're going to be all the way up here at 3. So this graph of y equals 3 sine x is going to go from 0 all the way up to 3. Now at 180 degrees, sine x is back at 0 again, and 3 times 0 is 0. So this graph of y equals 3 sine x goes all the way up to 3, but then comes back down to 0. And then at 270, where sine x would have the value negative 1, multiplying that by 3, we're going to have a value negative 3. Okay? And then it will go back down to 0 again. So what this transformation has the effect of doing is stretching out this graph in the y direction. Let me see if I can make a decent stab at sketching this. Oh, that was actually not too bad. Goodness. Just luck, I think. So that's the graph of y equals 3 sine x, and it has the same shape as y equals sine of x, but just stretched by a factor of 3. So by multiplying sine x by a number outside, that's like an expansion or a stretching in the y direction. If the number was less than 1, it would be a compression. Okay. Right. Let's talk next about this number over here. Okay. And let's imagine we're asked to sketch y equals sine x plus 2. All right. So let me do the same as before. Just going to sketch this. Okay. It's good practice actually just to sketch graphs, you know. I'm not a mathematician by training. I'm a physicist, but many physicists and mathematicians are much happier dealing with pictures than they are dealing with lots of numbers and so on. So maths at a professional level is very much often a kind of graphical, pictorial subject, and that's because of the amazing set of symmetries and patterns that exist in maths, and those tend to be more visual things than things that just appear in numbers. So again, let me just sketch as I say, the ghost of sine x. So here's sine of x, sort of lurking in the background. Goes between goes from 0 up to 1, back to 0, negative 1, back to 0. But we now have to draw the graph of y equals sine x plus 2. So at every point, I don't multiply sine x by anything, but I add 2 to it. So at the origin then, the value was 0. I have to add 2. So this graph is going to start at x equals 0 at a value of y which is equal to 2. As sine x goes up from 0 to 1, if I add 2 to that, you see I'm going to reach the value 3. Sine x comes back down to 0, so this will come back down to 2. And then at 270 degrees, where sine x has the value negative 1, when I add 2 to that, I get 1. And so this graph of sine x plus 2 is going to dip down to the value 1, which is negative 1 plus 2. And then finally, as we get back to 360, where sine x is 0, this graph of sine x plus 2 will end at 2. And so if I can just sketch this. Okay, that's not too bad. That's sine x plus 2. And you can see the effect is to shift the whole graph up by 2 units. I've done these two first, dealing with the multiplying of sine and then the addition bit, because these are kind of a lot easier to think about than these rather tricky ones inside. This is expanding in the y direction, this is shifting in the y direction. Things get a bit harder when we think about what's going on inside the function. So let's have a go at this transformation here where a number is multiplying x. Let's imagine we have to draw the curve y equals sine of 2x. Okay? And let's imagine again that we are working with the same range of x, 360 degrees. So let me just sketch this axis. Okay. It's going to go between -1 and 1. And we said that we would sketch it between 0 and 360, okay? So there's 360, here's 90, 180, and 270. Now I'm actually also going to put on here 45 degrees for a reason that will become apparent very quickly, and also 135 degrees. Okay. I'm not going to draw the sketch of sine x on here because it would actually be too confusing, but we can just refer to the little sketch of sine x that I've got over here. So what we know about sine x is the following. If you give the sine function 90 degrees, it's going to return to you the value 1. Okay, so if I can sort of sketch maybe down here in a different color, you can think of the sine function as, I like to talk about it as a little machine. Just has the word sine written on the side, and it has a tube that you put things in, and it has a tube where stuff comes out. And what you know is that if you put 90 degrees into this machine, the cogs will turn and it will spit out the value 1. Okay. So here's the really important point. Because we want to plot the graph of y equals sine of 2x, do you see that if I choose x to be 45 degrees, twice x is 90 degrees, that gets fed into the sine machine and it's going to spit out 1. So at 45 degrees I'm going to get the value 1, because what I'm putting into the sine function or the sine machine at 45 degrees for x is twice that value, which is 90 degrees. All the function sees is what you put in, 90 degrees. It doesn't care about x. It cares about what you're putting in. And because we have 2 times x, all it sees is 2 times x. So when x is 45, this function sees twice that value, which is 90 degrees, and it knows, oh, you've put in 90 degrees, I'm going to give you 1. Now, when you put x equal to 90 degrees, in this function we're sketching, we have to double it before we put it into the sine machine. So we double 90, we get 180. And we see on the sine curve that when you put 180 degrees into the sine function, you get 0. So this function, if you give 180 degrees, it will spit out 0. Okay. So again, at 90 degrees for x, because we're doubling it before we put it into the sine machine, it's going to return the value 0. 135 degrees for x, if it's doubled, gives 270. We're feeding 270 into sine, and for sine 270, it will give you the value -1. So for x equal 135 degrees, for this function sine of 2x, it gets doubled to 270, fed to the machine returns -1. And finally at 180, we double that to 360, sine of 360 is 0. So you see what's happened is that by trying to draw the graph of y equals sine 2x, we see that we have the entire sine curve in the first 180 degrees. And when we go above 180, when we double, we are into angles that we haven't talked about yet. So the angles will be bigger than 360. So you'll have to take it from me. We're going to talk about this more in the next tutorial, that this sine function just continues forever. It just wiggles the same way forever. And so if you know one whole cycle, you can just keep repeating that. So what's going to happen here is that this will just repeat. Okay. Like that. So that is the graph of sine of 2x. And the key point is, the reason it's tricky when you deal with these parameters inside the function is they kind of do the opposite to what you might think. So you might think, oh, sine of 2x, it's just going to expand it in the x direction. No, it compresses it. So multiplying sine by a number, it really does expand it according to that number. But multiplying the x inside sine by a number, it has sort of the opposite effect. So multiplying x by 2 compresses the function by a factor of 2. So we go from, let me maybe just sketch the ghost of sine after all, now that we've done this. Here's what sine of x would have looked like on that graph, and you see it's been compressed by a factor of 2. Yes, tricky that, and it needs intuition about what functions really do. So hopefully I've managed to get across why it has this shape. Let's just do one more example. Let's do y equals sine of x. What shall I do here? I think I'm going to do x minus 30 degrees. Okay. So I'm looking at this parameter here. If you shift x, and we'll just again do it between 0 and 360. You'll get very used to plotting these graphs, you know, after a while. So here's 90 degrees, here's 180, 270, 360. Curly x, please. This is going to go between -1 and 1. And again, we have to sort of think about, what does the function see? Well, we know that if the function sees 0, then it gives you back 0. If you give 0 to the sine function, it's going to spit out 0. But do you see here that if I set x to 30 degrees, because I'm subtracting 30, then the function's going to see 0. So actually, at 30 degrees here, the function is going to see 0, because x is 30 degrees, we subtract 30, and we're going to give 0 degrees to the function, it's going to spit out 0. If you give the function 90 degrees, it spits out 1. But for this function to see 90 degrees, x is actually going to have to be 120. Then, at x equals 120 degrees, we're asked to plot this function. We subtract 30, then we feed it to sine. So 120 minus 30 is 90. We feed 90 degrees to the sine machine, it spits out 1. And so on and so forth. So essentially we're shifting the whole function over by 30 degrees. Okay. When x is 0, we have the sine of negative 30 degrees. Again, we haven't talked about angles outside of the range, so just take it as read from me that that would give a value of -1/2. Okay. What you would be happy with, I think, is that if we fed x as 60 degrees, then 60 take away 30 is 30 degrees, and we know sine of 30 is 1/2. So we have that point there as well. Okay. So what's happened here then is that everything has been shifted over, and it's a bit hard to draw actually. Do my best. Okay, not very good, but good enough, I think. So sorry about rather rough drawing here. But the point is that this sine curve has been shifted in this direction by 30 degrees. And again, it's a bit counterintuitive because you might think when you see x minus 30, oh, I just have to shift it by minus 30 degrees. No, you do the opposite. So when you shift the function sine or cosine by an angle, when you plot the function sine or cosine x with a shifted angle, the graph moves in the opposite direction to what you might naively think. So when we plot x minus 30 degrees, we are actually shifting the whole function to the right. If we had x plus 30 degrees as the thing we were plotting, sine of x plus 30, it would shift to the left. So this is quite a tricky topic, and sometimes you might combine, some of these transformations together. So you have to sort of pick them apart using your best judgment. But once you understand these 4 different transformations, I think you'll have no real trouble looking at combinations. So I hope that's been helpful, and in the final 2 tutorials we're just going to look at solving trigonometric equations using 2 different methods, and I'll be talking more about sine x and cosine x as functions. Right, so I'll see you next time.